A plain composite body in the form of a hand fan is formed by attaching a thin uniform rod of mass 3m and length 2a to a uniform circular disc of mass 2m and radius a. The composite body is free to rotate in its own plane about a fixed horizontal axis perpendicular to its plane and passing through the midpoint of the rod. A. Show that the moment of inertia of the composite body about the axis is 10 ma squared. B. Find the radius of gyration of the body about this axis. While in its position of stable equilibrium, the body is given a small horizontal push on the disc so that it oscillates through small angles in a vertical plane. C. Show that the equation of motion can be expressed in the form 5a d theta on dt all squared equal to 4g into cos theta minus 1, where theta is the angle through which the body turns in time t seconds. D. Find the period of small oscillations and the length of the equivalent simple pendulum. Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at this question from the Southwest Regional Mock 2024 Further Mathematics paper 3, and it was question number 8. So it was from rotational dynamics, one of the topics that students have difficulties in when it concerns further mathematics with mechanics and probability. So guys, make sure you follow the video from the beginning till the end. Without wasting much of your time, let's get started. Okay, so we are going to solve the equation part by part. We have to first of all show that the moment of inertia of the composite body about the axis is 10 ma squared. Now the composite body is basically a body that consists of a thin uniform rod and a uniform circular disc. So the combination of a rod and a disc. Okay, so to get the moment of inertia of any composite body, we start by drawing out the body and indicating the axis, then using our theorems of moments of inertia to get the moment of inertia of the composite body about the given axis. So here we have a combination of a rod and a disc. So we have the rod and then we have the disc. Okay, so the is in form of a hand fan. You know what a hand fan is, right? So basically the disc will be attached to one end of the rod. I can call the end of the rod maybe the end to the right. You could also attach it to the left. It all depends on you. So this rod has length 2a and mass 3m, while the disc has radius a and mass 2m. Now the given axis here is perpendicular to the plane of the lamina, that's the plane of the composite body, and it's actually perpendicular to the plane, and it is passing through the midpoint of the rod. So I could maybe just indicate for convenience that this is the axis. I can call the axis delta, is perpendicular to the plane, and then it is passing through the midpoint of the rod. Okay, so we need to get the moment of inertia of the composite body about the given axis delta. So since it is passing through the midpoint of the rod, it therefore means that it's going to divide the rod into two equal parts. So this length to the left is going to be a, and the length to the right is also going to be a. Okay, now the moment of inertia of this system, or this composite body about the axis delta, we can call it is. We need to take the moment of inertia of the rod about the axis and we add it to the moment of inertia of the disc about the axis, since the composite body is purely made up of the rod and the disc. So this is a rod disc system. Okay, now we are going to find the moments of inertia of the rod about the axis, then later we find the moments of inertia of the disc about the axis. So let's begin with the rod. The moments of inertia of this rod about the axis can be interpreted as the moments of inertia of the uniform rod about an axis passing through the center and perpendicular to the rod. okay, and the standard formula exists, which you can check from your formula booklet. So standardly, the moments of inertia of any rod whose mass is m and whose length is l about an axis passing through the center and perpendicular to the plane of that rod is given by ml squared divided by 12. Okay, so m is the mass and l is the length. So this can be gotten by integration, but since the equation didn't ask us to get it by integration, we can just use the standard results. Okay, so we need to replace the mass of the rod with 3m and we replace the length of the rod with 2a. When we simplify, we get 3m on 12 is just m on 4, and then we have to square 2a to get 4a squared. So 4ma squared in the numerator divided by 4, since 3 on 12 is 1 on 4. The 4 cancels and we get that the moment of inertia of the rod about the axis passing through the center and perpendicular to it is ma squared. Now we need to also find the moment of inertia of the discs, okay, of these discs about an axis passing through A. That's about the axis passing through A. So to get a moment of inertia of these discs about the axis passing through A, we could use a parallel axis theorem, and that theorem says that if we want to get a moment of inertia of a certain body about a certain axis, then we need to take the moment of inertia of that body about an axis passing through the center of the body, and then we add it to the mass of the body times the square of the distance separating the two parallel axes. So I can call the axis passing through the center of the disc as the axis C. The distance separating the axis delta and the axis C is basically A plus the radius of the disc, which is also A, right? So we are going to get 2A. So the distance separating the center of the rod and the center of the disc is basically 2A, because we need to add this A here plus the radius of the disc, since the axis C is passing through the center of the disc. So that distance separating the two axes is 2a. So from the parallel axis theorem, the moment of inertia of this disc about the axis delta is equal to the moment of inertia of the disc about an axis passing through the center plus the mass of the disc times the square of the distance separating the two axes. So from here we know the standard results for finding the moment of inertia of a disc about an axis passing through its center is the mass of the disc times the square of the radius divided by 2. Like I said, we just need to use the standard results. No need to use integration to derive it again, since we have not been asked in equation to do so. So since the standard results exist and you can get it from the formula booklet, we just need to do numerical application. So md here stands for the mass of the disc and arrow stands for the radius of the disc. So the mass of the disc is 2m and then the radius of the disc is a. We just need to replace, so we get 2ma squared on 2 plus 2m times 2a all squared is 4a squared. Now here we are going to have ma squared and here we have 8ma squared. When we add together we get 9ma squared. So it therefore means that the moment of inertia of the system, which is the composite body about the axis passing through the center of the rod, is equal to the moment of inertia of the rod about that axis, which is ma squared, plus the moment of inertia of the disc about the axis, which is 9ma squared. Adding up, you get 10ma squared. Therefore, we can conclude that the moment of inertia of the composite body about the given axis is 10ma squared. So the proof is complete. Okay, now the next part of the equation, though we have missed one part of the equation which was talking about finding the radius of gyration. I don't know what. Anyways, I am going to because you just have a formula to use. Okay, the formula is clear. The radius of gyration is equal to the square root of the moment of inertia divided by the mass of the system, and the mass of the system is a sum of the mass of the individual bodies in the system. So you just need to use that formula to get your radius of gyration. So the moment of inertia was 10ma squared and then the mass of the system is 3m plus 2m, which is 5m. So with that we can get it. Anyways, let's proceed to the next question. I will lay more emphasis on this in the comment section so that you also know how to find the radius of gyration. I don't know if the formula is in the formula booklet, but anyways, I think it is there. Now, the C part of the equation says that we should show that the equation of motion can be expressed in this form. Now, let's get back to the equation. Let's come here. While in its position of stable equilibrium, the body is given a small horizontal push on the disc so that it oscillates through small angles in a vertical plane. Okay, now we saw that theta is the angle that the disc is going to turn, okay, after a certain time t in seconds. And initially the axis, remember that they said the composite body is free to rotate in its own plane about a fixed horizontal axis. So initially the body was actually vertical since the axis is horizontal, because we know that the axis must be perpendicular to the plane of the lamina. Okay, I just represented it this way originally just to find the moments of inertia, but to analyze this second question we have to redraw a diagram. Okay, so than to be drawing these things again, I'm just going to represent this system just with a line. Okay, anyways, I'm going to explain because I cannot draw everything again. It's very tedious to prepare something like this. So for the sake of time and also energy invested, I'm not going to draw everything. I'm just going to indicate the whole system just with a line. Okay, so first of all I need to indicate the axis. The axis is delta and it's horizontal, and the axis is always the line of zero potential energy. So this OPE here is zero potential energy. Now initially, like I said, I am going to indicate the whole system with a line. Okay, I'm not going to draw everything again. So this is the initial position. Okay, noting that actually this axis is passing through the center, though it is I have not drawn to scale, but note that this axis is passing through the center of the rod. Okay, so initially the body, the composite body was vertical. Then since it is vertical, actually we know that the center of mass or the weight of the whole body will be concentrated at a certain point. Okay, we can put a point here, and the weight is going to be 5 mg, because we need to add 3m to 2m to have 5m as a mass, but the mass is concentrated at its center of mass, so the weight is 5 mg. Like I said, this line here is just representing the whole system. That is a combination of the rod and the disc. Now this point here is the center of mass, where the mass of the whole system of the composite body is concentrated at. Okay, so initially it was like this. Okay, then now it was now giving, remember it was giving a horizontal push, and the horizontal push was on the disc. It therefore means that initially the disc was actually below the axis, because if you want to push it, we are going to push it and it's going to rotate in this direction. Okay, so it was given a horizontal push on the disc, and is normally rotating. Omega here is the angular velocity, that is change in angular displacement. The angular displacement is theta. Okay, so at a certain time t, it is now in this position because it has turned an angle theta with respect to the vertical, since originally it was in the vertical position. So the mass is still concentrated there, therefore 5 mg is still the weight. Now with respect to the vertical, the angle that has been turned is the angular displacement, which is theta. Okay, and then omega here is theta dot, which is the angular velocity, that is change in angular displacement with respect to time. Okay, now initially we have that the distance from the center of mass to the line of zero potential energy is x bar. We are going to find the value of x bar. All right, so how do we then get the value of x bar? First of all, we are going to consider moments. To get the value of x bar, that's the distance from the center of mass of the system to the line of zero potential energy. We call that distance x bar, and we are going to use moment. So first of all, I need to indicate the mass of everybody here. We have the disc, the mass is acting, the mass is 2m, and the weight is acting at the center vertically downward, so we have 2 mg. Now the center of mass of the mass of the whole system is concentrated at this point here. okay, and this point will have weight as 5 mg, since the mass of the whole system is 3m plus 2m, and we need to multiply by g. And now the axis itself is the center of the rod, where the weight of the rod is acting, so we have 3 mg for the weight of the rod. Okay, now we need to take moments about the axis delta, and when we take moments about the axis delta, we just have that the clockwise moment equal to the anti-clockwise moment. But clearly from here you realize that you realize that this 3 mg here will have no moment, since it is acting on the axis, right? So there is no perpendicular distance from 3 from the weight 3 mg to the axis, since it is acting on the axis. But 5 mg has a perpendicular distance of x bar, and then 2 mg has a perpendicular distance of 2a, because the distance from the axis here to the center of this disc was 2a. We saw it previously. So if we take moments about that, we are just going to have 5 mg times x bar to be equal to 2 mg times 2a, okay? Or in fact, we can just say that the moment of the whole body is equal to the sum of the moments of the individual bodies, so about the given axis. So the moment of the whole body is just 5 mg times its perpendicular distance, which is x bar, and then the moments of the individual bodies we have for the disc, we need to take 2 mg times its own perpendicular distance, which was 2a. Then since the moment of the rod about the axis passing through the center is 0, since the weight of the rod is acting at the center, from here we can get x bar. X bar will give us 4a divided by 5, when all m and g will cancel, and then now we need to divide both sides by 5 so that we get the value of x bar. So this x bar is a distance from the center of mass of the body to the line of zero potential energy. We need it, okay, because we need to apply the principle of conservation of mechanical energy. So the kinetic energy normally is half times the moments of inertia of the system times omega squared, and then the potential energy is mgh, where this h here is the displacement from the center of mass of the body to the line of zero potential energy. So the principle of conservation of mechanical energy says that the initial mechanical energy is equal to the final mechanical energy, but mechanical energy itself is a sum of the kinetic energy and the potential energy. So we are going to fill this table where we are going to find the initial and the final kinetic and potential energy respectively. So for the initial kinetic energy, initially the body was at rest, okay? So because for the initial kinetic energy we need to replace omega here with omega initial, but since omega is theta by dt and initially the angle was constant, the angle was not changing, okay, when we differentiate the angle we get 0, so the initial kinetic energy is 0. What about the final kinetic energy? The final kinetic energy is half times the moment of inertia of the system times omega squared, because at this point now it has an angular velocity of omega, which is the change in this angular displacement with respect to time. You see theta was now varying, okay, at a particular time. So the moment of inertia of the system, we proved previously that it was 10 ma squared. So when we simplify this, we get 5 ma squared times omega squared. So that is a final kinetic energy. Now what about the initial potential energy? Potential energy initial is basically the mass times g times h initial. What is h initial? H initial is x bar, okay. We said h is the displacement of the center of mass of the system from the line of zero potential energy. Displacement is a vector quantity. Since it is below the line of zero potential energy, then it is going to be negative, okay. So the initial potential energy is negative, the mass is 5m, and then times g, okay, and then now times x bar. The x bar is 4a on 5. When we simplify, we get negative 4m ga. So that is the initial potential energy. Now we need to find the final potential energy, but to get a final potential energy we need to take the mass times g times h. What is h? H is the distance from the center of mass of the body in its final position to the line of zero potential energy, and it's actually this distance, okay, and this distance is basically the same as the adjacent of this right angle triangle whose angle is theta with the vertical and whose hypotenuse is x bar. So to get h, we need to use SOHCAHTOA, and if we take the cosine of the angle, we need to get the adjacent divided by the hypotenuse. The adjacent is h and the hypotenuse is x bar. So from there we get h to be x bar times cos theta. So the final potential energy will be, since the distance is below the line of zero potential energy, then it is negative since it is displacement. So we have negative 5 mg, that is for the mass times g, and then h is x bar cos theta. X bar is 4a on 5, so we have 4a on 5 cos theta. Once we simplify, the 5 will cancel and we are going to get negative 4m ga cos theta. So we replace that in the table. Okay, now from here, now we need to apply the principle of conservation of mechanical energy. So it says that the initial mechanical energy is equal to the final mechanical energy. The initial mechanical energy, we need to sum the initial kinetic and the initial potential. When we sum, we just get the initial potential since the initial kinetic is 0. And for the final, we also need to sum the final kinetic and the final potential. So doing that, we are going to get negative 4 mga to be equal to negative 4 mga cos theta plus 5 ma squared omega squared. We need to add 4 mga cos theta on both sides. When we add it to this side, we get this. When we add it to this side, it cancels with this, and then we get this. Now we can divide all through by ma. Okay, ma will cancel ma will cancel, m will cancel, and then a squared on a is just a. From there we can basically factorize 4g, and then the proof comes out as 4g into cos theta minus 1. Oh, there is a g lacking here, so we need to, there is a g lacking here, so I think this space here was actually for the g. So doing that, we basically have the proof, since omega squared is d theta by dt all squared, because omega is d theta by dt. So we have proven that the equation of motion of the body in ensuring motion is actually 4g into cos theta minus 1 equal to 5a d theta by dt all squared. So you see the importance of us looking for the distance of the center of mass of the whole body from the axis. So we're not just looking for it like that. So please, in every equation, always find the distance of the center of mass of the whole body from the given axis, especially in cases where we have a combination of bodies, because if it was just the rod, then the center of mass will be at the center of the rod. If it was just a disc, the center of mass will be at the center. But now we have a rod and a disc combination, therefore we need to find the position of the center of mass of the body. Okay, now the last question says we should find the period of oscillations and the length of the equivalent simple pendulum. So this is the previous proof we have. Now for simple harmonic motion, we know that the acceleration is always the acceleration is defined by theta dot dot equal to negative omega squared times theta. Okay, theta dot dot is actually the angular acceleration, theta is the angular displacement, omega is the angular velocity. So this is the relationship that we are going to use. Now what about the period? The period is 2 pi divided by omega, and it is also 2 pi the square root of L over G if we want to approximate the motion to the motion of a simple pendulum, because a simple pendulum oscillates and the motion involved is simple harmonic motion. So I'm going to analyze and I'm going to leave the rest to you to calculate. So for us to come out with this relationship here, okay, we must differentiate the equation of motion that we have. So if I differentiate this equation, I'll be differentiating with respect to time. So when I differentiate the left hand side, since the left hand side is not in function of time, once I differentiate, I'm going to add d theta by dt, which is theta dot. Okay, that is called chain rule. When you're differentiating something that is not with respect to, that is not in terms of time, for example, we need to add something else to it that will balance up, okay, because this is in terms of theta, right? So for a little explanation, if we have something r to be equal to a function of theta, let me say f of theta, all right, and then I ask you to find the r by dt, okay. If I say find the r by dt, you realize that you cannot just differentiate and have f prime of theta. No, you are going to say the r by dt is the same as the r by the theta, because r is in terms of theta, so you can actually differentiate r with respect to theta, and then you multiply it with the theta by dt. You realize that the thetas can still cancel and you are still left with the r by dt. So this d theta by dt here is what we call theta dot. So the left hand side here is actually in terms of theta, also the right hand side as well, but the right hand side is in terms of t. Is okay because theta dot here is the theta by dt. So when we differentiate, we are not going to add any theta dot again, but we are going to add theta dot to the left hand side, okay, because it is not in function of, it's not in function of time. Okay, I guess you have copied this already. So if we differentiate the left hand side, remember we need to differentiate and then we attach theta dot, which is the theta by dt. So once we do that, we get 4g. When we differentiate cos theta, we get negative sine theta. Then we need to attach our theta dot. Now when we differentiate the right hand side, we keep the 5a. When we differentiate theta dot squared, we need to drop the power. Then we take theta dot to the power 2 minus 1. Then we differentiate theta dot. That is it. It's also chain rule. It's like you have maybe r to be equal to x squared, and you want to find the r by the x. Okay, so the r by the x, in fact I can start by maybe if I let u to be equal to x, okay, anyways, let's just use something simple. If you want to find the r by the x, what are you going to do? To find the r by the x, you are going to say the r by the x is equal to, now you need to drop the 2, then you take x raised to the power 2 minus 1, then you also differentiate x with respect to itself. That's basically what is always done, but because when you differentiate x with respect to itself, you get 1, okay, then you just, at the end of the day, you're just going to have 2x. So in this case, for us to differentiate theta dot squared with respect to time, okay, we are going to drop the power because theta dot is actually the theta by dt. So if I want to differentiate the theta by dt, so I want to differentiate with respect to time the theta by dt all squared the theta by dt. Don't mind I'm taking time to explain this, I just want you guys to understand. The theta by dt all squared, what do we need to do? We need to drop the power, which is 2, then we multiply it with the theta by dt raised to the power 2 minus 1, which will just give us the d theta by dt. Then we now differentiate the d theta by dt with respect to time, okay, and when we differentiate d theta by dt with respect to time, we get the squared theta by dt squared, and the squared theta by dt squared is like the second derivative of theta, which is theta dot dot. Okay, so this d theta by dt here is just theta dot, that's the first derivative of theta. So the number of dots there represent the number of derivatives. So theta dot is the first derivative of theta with respect to time, and theta dot dot is a second derivative. That is why here I also attach a theta dot dot to it. Okay, now from there, what do we see? We clearly see that the theta dots are going to cancel, right? Theta dots are going to cancel clearly. So once the theta dots cancel, we now have a very nice equation. We are going to have 4g into negative sine theta to be equal to 5a times 2 theta dot dot. Okay, now remember that we are dealing with small angles because theta is a very small angle according to what the equation says, and for small angles sine theta will always approximate to theta. I believe even math students know this. So small angle sine theta approximates to theta. I just need to replace sine theta here with theta. Okay, I can even divide both sides by 2, so that I get 4 on 2 to give me 2, but it's a negative, so we have negative 2g times theta to be equal to 5a theta dot dot. So at the end of the day, what do we have? Theta dot dot is negative 2g on 5a times theta. Now compare with this equation, you realize that theta dot dot is there, the negative sign is there, so what is going to be omega squared? Omega squared will give us 2g divided by 5a, since theta and theta are the same. So now, since you have omega squared, then you are going to find omega, okay, by just taking the square root of this, the positive square root. We ignore the negative square root. Okay, now when you get omega, I think you can already get the period. The period is 2 pi on the omega you are going to have. Now once you get the period, you can now get the length of the equivalent simple pendulum by equating that period to 2 pi root L on G and finding L, that is making L the subject of the formula. In fact, if you just equate these two equations here, you realize that 2 pi will cancel 2 pi. You can square both sides and automatically you get L, since you just replace omega squared with what you have here. Okay, that is if you're dealing with these two equations here, the 2 pi cancel 2 pi, then omega will give you the square root of G on L, and then now you proceed. But anyways, like I said, to complete the equation, find the value of omega. Okay, once you find the value of omega, you're going to get the value of the period, which is taking 2 pi divided by your value of omega. It's going to be in terms of G and A. Now, how do I get the length of the equivalent simple pendulum? I need to come back and replace a period here, and then I equate it to 2 pi root L on G. Okay, and then I square both sides and I make L the subject of the formula. I'm going to get the length of the equivalent simple pendulum. Okay guys, thank you once more for watching. Make sure you like the video. There are so many videos on rotational dynamics in this channel, and if you are new to this channel, make sure you check the comment section and also check the description of this video. I'm going to indicate the links to all those videos so that you can follow them and watch. See you guys in the next video.